Today, my name is Badea Lepadatescu. I will present a paper with a title Theoretical Contribution regarding the modeling of the superfinished process. As an introduction, the topics are introduction, development of theoretical model of superfinished process, kinematic of current point of the tool in relation to the part, and conclusion. As an introduction, the study of kinematics of a point of the abrasive tool on the surface of the part arose from the need to know the shape or length or trajectory of the grain during rotation of the part. This is necessary to determine the parameter of the chipping regime to the length of the curve generated by the particle of the abrasive tool on the surface of the part to observe which element intervene in the chip equation of the trajectory of the movement of an abrasive grain to intervene on them to optimize the chipping regime. Also, based on the ratios in between obtained by to determine the space traveled by the abrasive grain, the respective velocity and acceleration can be determined by differentiating with respect to time, and it can be observed done during the entire processing. These parameters have variable values over a period. This fact leads to a variation of the parameter of the cutting regime and explains the fact that the roughness obtained after processing is not constant over the entire surface of the piece. The method of generating the oscillatory movement correctly used in production are mainly the mechanical and pneumatic arms that use the simplicity of the realization and softening operation. Development of theoretical model of superfinishing process. The theoretical model explains the phenomenon of automatic interruption of the chipping process during superfinishing through the prism of the intervention of the chipping liquid characterized by the ease with viscosity. The presented theoretical model explains the fine roughness of the superfinished surface by cutting the micro aspects that form the rough profile of the part left by over the previous processing operation. It also provides an explanation of the self-interruption of the chipping process. It is considered that the cutting process is interrupted automatically when follows the repeating of the tips of the initial geometric micro aspects. The proposed theoretical model starts from the following specifications. The active part of the abrasive grain, not embedded in the bender, has dimension comparable to the maximum height of the micro aspects, about 5.4 micron, that form profile processed part. The chipping liquid present in the processing area can be assimilated with the continuous environment of spherical particles that try to form an absorption layer on the surface of solid bodies, but to the dimension close to those of micro-relief of the part. They fail to penetrate in micro-aspective profile. The first second of the superfinishing process, the abrasive granule squeeze the oil drops from the surface of the piece, making the contact between the granule and the metal ridges, simultaneously achieving the cutting of the metal tips and the blunting, breaking, or tearing of the abrasive granule from the binder. The part of the metal tips can be fragmented and pulled from the matching area by cutting liquid, and others remain and penetrate in the depth of the valley. The alternative movement of the tool favors the stuffing of the chip pulled in the micro-relief of the part. In the next 10 seconds of matching, abrasive removes the entire layer of material that constitutes the initial micro-relief and begin to dig into the compact material. The traces left by the abrasive grains in the mechanical part are proportional to the size of the active part, and therefore much smaller than those left by the abrasive grain in the body of the rectified. So roughness of matching surface is much smaller. You can see in this first phase of the matching. The peaks of the superfinished surface are much more frequent and finer, so this bearing surface is larger and the pressure lower. The oil particles are no longer persist, and the superfinishing process is much more difficult. At the same time, the impurities settled in the microstructure valley contribute to the hardening of the surface layer. Thus, the abrasive grain can no longer detach chips, and the matching process stops after approximately 200 seconds. Kinematic of the current point in two relation to the part. Superfinish with the plunge. The first is superfinishing with the plunge field. During the processing of the part by superfinishing, the abrasive grain describes trajectories of different shape and length on the surface of part. The length of this trajectory is considered to represent the degree of coverage of the disc surface with traces of the processing. There is no direct link between the degree of coverage and the quality of the surface of the piece, in the sense that with the increase of degree of the coverage, the roughness of the surface, the bearing coefficient, the state of surface layer improve. An abrasive particle has a periodic sinusoidal movement during processing, whose equation is, you can see here, where the omega is angular velocity of the part. The radius vector OM will be projected on the three coordinates resulting in system 2. The projection on the OZ axis is 0 because the both part and the tool have no logical displacement. In the system substituting 3 and 2, we get the system 5, and differentiating with respect to time, we have obtained velocity. To find out the length of the trace of the trajectory on abrasive grain on the surface of the part, unfold the surface on the part and work in other system coordinate with working with variable r tau. Processing the relation and considering that only the length of the trajectory of the abrasive grain will be taken into account at one rotation of the part, then the limit of the parameter will be in the 0 and 2 PR will result in the formula 14. From relation 14, it can be seen which factor lead to increase in the length of the trajectory of the abrasive grain on the surface of the part, because the quality obtained after processing is directly proportional to his length. The amplitude of the oscillatory movement also has an important influence, because as the amplitude increases, so does the quality of the processed surface. The value of the amplitude of the oscillatory movement cannot be too high because it is limited by technological and functional consideration. The technological considerations are given by the need for small grain stroke, because the space between the grain does not allow for accumulation of the large volume of chip resulting from chipping. Functional and constructive considerations are related to the complexity of realizing a greater amplitude of the work system and the large moment of the inertia that may occur. That is why the optimal amplitude is 1 to 3 mm. Second is superfinishing with true feed. If the length of the processed part is greater than the length of the abrasive bar, then in addition to harmonic oscillatory and plunge feed, the tool of the part must perform a longitudinal feed. For example, let's assume that the workpiece has a rotation movement and true feed with axial speed V0. The abrasive bar has a harmonic oscillatory movement with an oscillating stroke and is pressed on the surface of the workpiece with a force P. In this case, the elements of the technological system are related to the Cartesian coordinate OX, YZ, and we determine the equation of the trajectory of the certain point M with abrasive grain. Thus, in from figure, the radius vector of certain point M of the abrasive tool is broken down into a component in 3 coordinates. The system relation 15 becomes and 16. Differentiating with the velocity, with the time, we obtain velocity. The arc of the curve described between the abscisses V1 and 2 has a length of 23. Calculating the length of the trajectory curve on abrasive grain at a single rotation of the part, and then integration limit in the 0 and 2p, we have relation 24. From relation 24, it can be seen that the length of the curve traced by an abrasive grain on the surface of the part will be greater if the amplitude of the oscillatory movement and axial speed V0 impressed on the tool or the part are increased. The amplitude of the oscillation cannot be affected too much, because a value higher of 3 mm would lead to a worsening of the evacuation of the chips and therefore the machining capacity of the abrasive grains. You can increase the advanced speed V0, or you can intervene on the angular speed omega of the part, which must not have value that lead to cutting speed higher than 35 meters per minute. The greater the length of the curve described by the abrasive grain, the higher the surface finish with mechanical surface. The second is the last one is the perfinition with 2 oscillatory movements. To increase the intensity of the machining process and intensity of the productivity of the process, it is recommended that the abrasive tool perform 2 types of oscillatory movement with different amplitude and frequencies. For example, an oscillatory movement produced pneumatically with smaller amplitude, 3 mm, and high frequency, cycle to 1000 cycles per minute, and another mechanically generated oscillatory movement with a higher amplitude till 20 mm, with a lower frequency till 150 cycles per minute. The composition of the two oscillatory movements increases the degree of the coverage of the matching surface with cross-hatch pattern of abrasive grains, resulting in a better surface finish in a shorter time. So, we will study the case where the oscillatory motion of the abrasive tool is composed on an oscillatory movement produced by a mechanical generator and another oscillatory movement produced pneumatically. The mechanical generation of the oscillation is produced by crankshaft slider plane mechanism used in figure 10. For the mechanism in figure 10, the explicit form of the displacement measurement is the next formula. The principal kinematic diagram of the mechanism with two oscillator mechanisms is shown in figure 11. From figure 11, it can be seen that the path left by the abrasive grain on the surface of the part is actually a composition of two harmonic oscillatory movements. The part has a rotational movement with angular velocity omega, and the abrasive tool is under the influence of two oscillatory movements, one with amplitude A1 and mechanical genetic by mechanism in figure 10, and another with amplitude A2 generated pneumatically. In order to obtain equation of the displacement of abrasive grain on the surface, everything is related to the system X, Y, Z coordinate system in figure 12. In figure 12, the radius of the vector OM is of a point of tool is broken down into following coordinating. You can see in the system, and considering this value, the relation becomes if the cylindrical surface of the part is unfolded in under C coordinate OZ, we have this figure 13. Using previous relation, we have this relation 31, and taking into account relation 30 and 31, the arc of path including between the axes U1 and U2 will have the length of 32. As a conclusion from the previous relation, we can draw the conclusion regarding the factor that influence the length S of trajectory of an abrasive grain on the surface of the part. Thus, it can be seen that the increase the length S of the trajectory of the abrasive grain, the angular speed omega 1 of the radius R, and the length L of the mechanical oscillation generation mechanism must be increased. Also, to increase the length S of the amplitude A1 and 2 of the two oscillatory movement can be increased. Also, from relation 32, it can be seen that the order of in order to have as long as possible the length of the curve S, we must reduce the factor K and therefore reduce the eccentricity A of the origin of the rotation movement from the mechanical center of the oscillation with respect to the axis of translation of the tool which support abrasive stones. Thank you very much for your attention.
Question.
F10?
F10, yes.